This is notes for compressible flow, isentropic, convergent, divergent nozzle flow. So in this topic, we will study about how to derive an equation, a set of equation to solve compressible flow for divergent and divergent nozzle flow. So before we go for the derivation, I would like to show you the convergent divergent. What we call as convergent and divergent is we have one section converging like this, and then we have a very small cross-section area here. We call it throat, and then this cross-section area again will increase, and we call it as a diverging section. So this design is similar with a venturimeter. I think you still remember what is venturimeter because we learned about it in Fluid Mechanics 1 very well. So what is the usage of a converging section is, so we have a convergent divergent nozzle here. So and then we have a reservoir of gas here. So, in real application, we connect convergent divergent nozzle with a compressor, with an air compressor here, and then we compress an air, we release that air to the converging section, and then when the cross section is become lower and lower, as you know, the basic idea of Bernoulli equation, the velocity will increase, and if your condition here is not compressible, means that the flow is not so high in velocity. So after the gas here go through the throat area, so the cross-section area become larger again. And for incompressible, so the velocity will decrease because the cross-section is increased. As we explained previously, if our speed is more than 0.3 Mach number, the phenomenon that occurs is compressible flow. So let's say we have a high pressure here and it could flow gas here more than 0.3 Mach number, so means it is a compressible flow. So when the convergent here, the cross-section area is becomes smaller and smaller, the velocity will increase, and at throat here the velocity will reach Mach number 1. So this is the common phenomena in converging and convergent divergent nozzle. So means that if you have a question about convergent divergent nozzle, you may take Mach number equal to 1 in throat area, and then if you give more pressure or increase the velocity in throat here will not increase more than 1. So what happened actually here is the molecule of gas here is start to compress itself. Mean instead of changing itself from lower velocity to higher velocity, when it's reach Mach number 1, it cannot flow furthermore in throat. It means the gas molecule will remain velocity as Mach number 1. So what happened here, if you give more velocity or give more pressure, the density of the gas here is start to compress. So means that the molecule distance between the air, between the molecule gas is start to stay in close contact to each other. So means that the density here will increase and increase and increase. So and then after, when the flow go to the diverging section here, so what happened? We know that we could imagine that we need more energy or high energy to compress the molecule of gas to to shorten its distance, molecule distance. So means that high energy after that, when the gas flow in diverging section, that energy will help or will uh, will push the velocity in diverging section into higher velocity. So in diverging section, the gas, the energy that compress the density will release into its velocity. So it could push, it could make flow in diverging section more than Mach number 1. So we call this one as supersonic flow because the Mach number is more than 1 in the exit. This is the usage of convergent divergent nozzle. So mean it's the basic idea is to create flow more than Mach number 1. However, most researchers want an exit velocity exceed Mach number 1. However, the presence of shockwave, later on we will learn about shockwave here, may lower this velocity. There are also other factors that can cause the exit velocity to not reach supersonic velocity. And this is the example in real application, the diverging nozzle, especially used in rocket engine here, or the converging nozzle that used in engine of jet. So the idea is to get flow more than Mach number 1, Mach 1. And this is the convergent divergent nozzle, again the real part of convergent divergent nozzle. And this is what I want to say here is this is the convergent divergent nozzle, so it has a special design. So and then when we give high pressure here, so the high pressure will convert into high velocity in the nozzle, in the throat here, so it could reach Mach number 1. As you could see here, the line will show it is Mach number 1. And then after this, so all researchers want to have Mach number more than 1 in divergent side, diverging section here. However, it's depend on the design, it's depend on type of gas, it designed on the existence of shock wave. So if, for example, we have a shock wave inside the nozzle here, or at the end, at the exit, or at the end of the divergent nozzle here, so we will not have Mach number 1 because the existence of shock wave will reduce the velocity, at the same time will give you Mach number less than 1. That's why we could see here that if the design is not properly designed, so the curve will not reach Mach number 1, and then it will go here. So around A and B area is the subsonic flow. And then if we could reach Mach number 1, it's depend on our luck actually. If you could maintain the curve here, and then the shock wave, for example, is not occur, or the shock wave will occur at outside of the nozzle, so you will have Mach number 1, Mach number more than 1. But if you have shock wave here in region D, for example, the shock wave occur inside the nozzle, so at the exit here you will not have Mach 1. So this is another chart to show the same idea, which at the throat here, the Mach number should equal to 1. And then it's go to the diverging section here, and then it's depends. Sometimes it could reduce to the subsonic flow, so means that it might be we have a design faulty of a lot of parameter will influence this. Or we could have a supersonic here, okay, and we have a shock wave to reduce it back. And in shock wave we have two type of shock wave. So we have a normal shock wave, which is perpendicular to the flow and or to the object, or to the oblique shock wave, which has a certain inclined angle. We will learn about normal shock wave up in the next lesson. So I hope you could read a little bit from your textbook the idea of convergent divergent nozzle. So the most important thing is in convergent divergent nozzle is in throat we need to have Mach 1, and then we need to do something to make sure that after the converging section we could get velocity more than Mach 1. So as the revision for today, for this lesson, I would like to compare or give you a table conclusion about what you need to know in compressible flow and incompressible flow and compressible flow. So for incompressible flow, the density is constant. So means we will use a value of density is constant, and it's normally usage for liquid. For compressible flow, the density changes. So it's normally used, or the in our syllabus we will focus in gas flow only. So and then if we compare in Mach number, we could say that velocity less than 0.3 Mach 0.3, so we could say that it is an incompressible flow. However, if our speed is more than 0.3 Mach number, so we need to assume that density has changed, and we need to calculate them by using compressible flow equation. So normally in incompressible flow, we keep using the SI standard of speed, meter per second. However, in compressible flow, in high speed, we normally use the idea of Mach number, means we compare the velocity with the speed of sound. And again, I would like to remind you that speed of sound will change according to type of gas, because you have a gas constant here, and then you have the specific ratio here, and then it depends on temperature. So means that you need to be alert. Sometimes the altitude will change the temperature, sometimes it stay on sea level, but you heat up the inlet, so the temperature is increased, then you will get a different speed of sound. So and then in compressible flow, we are using this one, volume flow rate. A1 V1 is equal to A2 V2, and the unit is meter cube per second. However, in compressible flow, because the density changes, so we need to put term of density in our continuity equation. So we must use mass flow rate. So the equation is rho 1 A1 V1 equal rho 2 A2 V2. So rho is the density, A is the cross section, and V is the velocity of fluid. So and then in incompressible flow, we are using Bernoulli equation. This one, I hope you still remember Bernoulli equation to solve about moving flow, about flow. So we have a pressure here, we have a velocity, and we have Z, the potential energy. However, in compressible flow, it is incorrect. It is totally wrong to solve compressible flow problems by using Bernoulli equation. Please remember this one. Please do not solve your compressible flow by using Bernoulli equation. Yes, it has density terms here, but you cannot change this density into rho 1 and rho 2. The rho here is constant, with the value of P1 V1 Z1 will change into P2 V2 Z2, but the value of rho here is remain constant. We don't have any rho 1 and rho 2 in Bernoulli equation. So what we need to do is we need to derive a set of equation, and then we need to use that equation to solve any problem in compressible flow. So after this, we will go for derivation of that equation.